So now, as we start to look at these molecules that I asked you to put together, ethane, propane, and butane, we're going to learn a new way to draw these, which is known as a Newman projection. And the advantage of a Newman projection is that it's a method for drawing that allows us to easily or more easily show the various bond rotations. And so what I'd like you to do with your model of ethane is to look at it and look, straight down that carbon-carbon bond. So in other words, if these are your carbons, then look at it in that direction. And what you should see is something that looks like this. Now your hydrogens may be in a different place from mine depending on what rotation you have, but you should be seeing something like this. This is our carbon in the front, and then this is our back carbon. And then while we know that those three groups coming off each carbon are not exactly planar, you can see I've drawn them so that the Newman projection draws them so that they're approximately planar. Again, we know that they're not exactly like that, but it's a close enough approximation. So we said earlier that some conformations are more important than others. When it comes to ethane, there's two conformations that are important. One is the one that I've already drawn. And the other one, we're going to rotate the carbon-carbon bond 60 degrees. And if we do that, we get a very different conformation. One that looks like that. The one on the left we call staggered, and on the right we refer to that as eclipsed. Now, which one is more stable? Because of all the infinite conformations of ethane that you could arrange with your model or draw, these are the two extremes. The staggered is the most stable, and the eclipsed is the least stable. So why is it? Why is it that the staggered is more stable and the eclipsed is less stable? All right, so there's actually several different reasons. The first one, although it does not apply to ethane, is what we would call sterics. This is when two, or sometimes more than two, atoms attempt to occupy the same physical space. And atoms don't want that. They don't really like that. In general, atoms want to be further apart. as you can see here. Now, how big of an energy difference is it between staggered and eclipsed? For ethane, the staggered is about 3 kcals per mole more stable. Now, that doesn't seem like a lot, but that's actually enough that the staggered is favored about 99% to 1 over the eclipsed. So sterics can be an issue. Now, they're not going to be an issue here with ethane. The hydrogens themselves are actually too small to have any sort of steric interaction. But as we get into larger molecules, such as ethane or butane, then sterics will come into play. We also have what's known as electrostatic repulsion, and this is the main contributing factor in ethane. So electrostatic repulsion means that when we align bonds, as we do in the eclipse conformation, at that point the electrons are close enough to repel. So both of these are reasons why the eclipsed is less stable than the staggered. But we also have another reason, a third reason, that kind of goes the other direction. This third reason is a reason why the staggered is actually more stable. And that's the idea of hyperconjugation. If you recall, hyperconjugation is something we talked about when we learned about carbocations. And so the same thing can happen, but only in a staggered conformation. So this sigma bond can donate into the sigma star, the empty sigma star orbital, for a bond that's 180 degrees away. We only get something that's 180 degrees away if we're in a staggered conformation. And so, as always, that idea of delocalizing electrons, sharing electrons, is a stabilizing effect. All right, so we looked at ethane, and so now we're going to look at propane. Before we do that, take your model of propane and sort of spin it around that carbon-carbon bond, and you can choose either of the carbon-carbon bonds. It's going to be exactly the same. But start to look at how those staggered and eclipse conformations look. So it ends up being very, very similar to ethane. The difference is we have a methyl group in one spot instead of a hydrogen. Does having a methyl group there make a difference? And again, this is a 60-degree rotation. Well, methyl is bigger than hydrogen. 4 atoms, often going to be bigger than just a single atom. And so now instead of 3 kcals, the difference in energy is 3.4 kcals per mole. And the reason for that is the larger size of the methyl group. Now we're starting to see some steric strain as well as the electrostatic repulsion. Now we're going to do this one more time. We're going to go up to butane. So again, take a look at your structure of your model of butane. And see what the different staggered and eclipsed conformations look like. Because for both ethane and propane, there was only one type of eclipsed or staggered. So if you had taken this eclipsed here and rotated it another 60 degrees, you would have ended up with something that looked identical to where we started. So again, take your model of butane and take a look at the possible conformational isomers there. And we're looking down this middle carbon-carbon bond. So you could start with this structure, and then I'm just going to start rotating by 60 degrees. Now you'll notice every time we rotate 60 degrees, if we started in a staggered, we rotate 60 degrees, that takes us to eclipsed. If we start with eclipsed and we rotate 60 degrees, we end up with staggered. So notice, even though this is another staggered, this is staggered again, in this case, this staggered conformation is not equivalent to the one we started with. Why is that? Well, look at the relationship of the two methyl groups. And you'll see in the first structure, the two methyl groups are completely opposite each other, while now they're next to each other. And we can rotate this one more time. To give us one additional conformation. We could keep going, and you may want to with your model kit, but if we keep going, we'll end up going back through structures that are identical to the ones that we have, and then eventually we'd get back to where we started. But notice now we have 4 different conformations, 2 that are staggered, 2 that are eclipsed. The staggered conformations are always better than the eclipsing conformations. But between the 2 staggered conformations, which one is better than the other? Well, the key is these methyl groups. When these methyl groups are near each other like this, we end up with what's called a gauche interaction. And while that's not as bad as an eclipsing interaction, it's still, less than ideal. And so with this gauche conformation, that's going to be less stable than this conformation on the left when the methyl groups are completely opposite each other. So when the methyl groups are completely opposite each other, This is called Anti-Periplanar, and this is the most stable conformation for butane. So now if we think about what that means, what would be the least stable? Well, we know it's one of the eclipsed, but again, take a moment or two with your models and rotate and go through the different conformations and see which one looks to you like it's the least stable. And so the closer we put large groups together, such as the methyl groups, the worse it's going to be. So down at the bottom, when the two methyl groups are eclipsed with each other, this is our syn-periplanar, or our least stable conformation for butane. So a couple things to remember here. First is just because one conformer is more stable than another doesn't mean that it's the only conformer that exists. All of these rotations are happening freely, but what it does have to do with is the relative percentages of the different conformers. The more stable a conformer is, the higher its population is going to be. And you may recall, and we won't go through the math right now, but you may recall that there was actually an equation that you learned in general chemistry that related the equilibrium constant, or the equilibrium ratio, to the energy difference. And so finally, you might ask, what about molecules more complicated than butane? And so I would suggest build a model of pentane, and then look down the C2, C3, the second and third carbon bond, and maybe put that into a staggered conformation. But your other carbons are still going to be able to rotate, and so you're going to end up with multiple different versions of that staggered conformation. And so basically what happens to us is, once we get into conformation or molecules more than about 4 carbons, we can't easily do this kind of analysis with just a model kit, and it generally requires computational software to do. But this whole idea of different conformers is going to become important in another number of other parts of this course, and so that's why we get this introduction here. So now you should get out in-class exercise number 14, which just gives you some practice drawing Newman projections, and work through those problems.